So up next, come to our fourth keynote session, and our fourth keynote speaker. We'll have Oskar Thorén, the independent researcher. So what Oskar is gonna share on is about mobile proving. So what is it so important about mobile proving is because they're able to do client-side proof on mobile natively. And Oskar has been writing about ZKPs at zkintro.com. So if you want to know him more, you can log into zkintro.com, exploring a Nova-based ZK VM, HyperNova, and trying to make proving on mobile easier. So I hand over the stage to Oskar.
Hi everyone, my name is Oskar. Is this on? Can you hear me? Yeah. So I'm going to talk about mobile proving. Briefly about me, independent researcher. Previously I founded Vac Research and created Vacu. Vacu is kind of a spiritual successor to Whisper, which is this peer-to-peer messaging protocol that was used in the beginning of Ethereum. We've been using CK on mobile for quite a while, using RLN for spam protection in peer-to-peer network, and recently been working on folding schemes. And current focus is writing about CK and mobile proving, which is the focus of this talk. So the TLDR of this talk is that we want to make proofs on mobile, and mopro is a toolkit for making proving on mobile simple and fast. And we want to make CKP on mobile great together. So we want to make proofs on mobile. Why do we want to have client-side proving? So for client-side proving, for technology proofs to gain widespread adoption, we need to be able to do proofs where users expect to be able to do proofs. Here's one example from Susalu, which was early this year. It's kind of a proto-network state, and they have this identity system called Zupass, which is kind of crypto-native CK identity. This was also used recently at Dev Connect in Istanbul, where you sort of had to prove that you were able to get access to co-working spaces and various events. They also had this kind of game where you were catching frogs, and it was quite successful in that you had like maybe 100,000 frogs or something that were caught. And this kind of game or this kind of gating, like for example, to get entry to this event or a co-working space or something like that, it basically requires that you are able to do this on a phone because people aren't going to walk around with their laptops, right? Another example is kind of real-world identity. So there's this system called Aadhaar, which is basically an identity system used in India. It has more than 1 billion users. And basically it's this. It's like a signed PDF document, RSA signature of a PDF document. And people use it for like things like rent and bank accounts and everything. And they basically give up their data to anyone to sort of prove who they are. And there's a PC project called Aadhaar, where basically they add CK onto this and create kind of a CK identity on top of this. So you can prove that you have a valid Aadhaar identity without revealing any specific details about it. There are other examples where we want to use client-side proving. So for example, any kind of private social network or something like that. For example, there's ECDSA, which is a popular thing that existed a while ago. Kind of any kind of fungible, like private transactions, private money, or something where you just don't want the whole world to sort of know what's going on. Then you sort of need some kind of user-signed proofs or something of that sort. So what kind of properties do we want from client-side proving? So there's a few of them. We want it to be trust minimized. So the user herself should generate the proof. It should be accessible, and most people are on mobile phones. They don't run around with a laptop or whatever. It should be robust. It should just work. Like it shouldn't be like all these hoops or all this weird stuff you have to think about. We want to have sort of to get adoption, mass adoption. We want to be able to support large groups, and this also means large anonymity sets. So if you look at, for example, Aadhaar, it's using more traditional cryptography tools like RSA signatures and stuff like that. Also ECDSA signatures in Ethereum or GitHub keys or whatever. And for this, these are kind of more complex to do client-side proofs on. So we also need to be fast as well. And finally, we want it to be developer-friendly. So it should be easy for developers to write circuits and applications for this. And when I say client-side proving or mobile proving, I mean specifically native proving. And you might ask, like, what about browsers? So there's a few reasons for this. So one is security. You sort of get more open system level security with sort of secure enclave and isolation and so on. And just like a reduced attack surface. And this is especially important if you like want to give up your private credentials, you don't want to just upload that to a random web view, for example, especially when we talk about real-world identity solutions. It's also more performant, so you get native performance in terms of hardware acceleration, and there's multi-threading and all this kind of stuff. And while you can get this to some extent on a browser, it's never going to be as good as native. Native is just always going to be better or more consistently robust. You also get better affordances, so you get access to things like secure enclave, push notifications, cameras, sensors, and so on, storage, all of these things that are sort of just better when you do things natively. There are some trade-offs, obviously. So if you just do a browser thing, a website, you don't have to release an app, which can be time-consuming. There's also some risk of censorship, for example, in the Apple iPhone store, but there's some workarounds around that as well. But these can also be complementary. So you can imagine you have a browser thing, but then also a native app for a better experience. And I think the biggest blocker for why people aren't doing things on mobile is just because it's extremely complex, especially when we talk about CK and doing kind of a good user experience with CK on mobile phones natively. And this is kind of where mopro comes in. So mopro is a toolkit for making proving on mobile simple and fast. And it's basically a set of libraries. I'll go through them in a second. It has a bunch of goals. So modularity, so it should be very easy to sort of add new proof systems as well as new platforms. So whether it's iOS or Android or React Native or Python or whatever. It should be developer friendly, so the developer can sort of just focus on the application logic and not worry too much about all this tooling stuff. Performant, as I mentioned before, it's just be like a very good user experience that's actually comparable to normal apps or normal identity solutions. And then finally, sort of multi-platform. So you want to be able to write your app and have it running on these different platforms at once. So whether it's iOS and Android, maybe some desktop thing, maybe some web app, whatever. So how does it work? This is kind of an architectural diagram. So I'll go into this a bit more in detail. I don't know if you can see it, but like basically at the top, you have circumcircuits, which are then plugged into this mopro core Rust library. And then it's talking sort of to the backend in terms of proving systems that's also written in Rust. And then the Rust library mopro core is exposing kind of bindings so you can talk to other language runtimes. And that's then consumed in a Swift library, for example, which then is consumed by an iOS application, and finally a user. And it's like a lot of stuff going on here, right? There's circumcircuits, mopro core, circumcompat, awkworks, unify, Swift library stuff. And the details are not super important, but what I'm going to do is I'm going to take like one thing at each layer and sort of give you an idea of what it looks like. So we start off with the circumcircuit, and this is like the main proof system we're using first, just because it's the most popular one, especially for client-side proving. So you have your normal circumcircuit that you use. You plug this into mopro core, which is the core Rust library. And it basically has these multiple adapters or middleware. And it's the first one is circum, but it's kind of trivial to add new proof systems. And then for the circum sort of middleware, it's using circumcompat, which is a way to translate the circumcircuit to the awkworks world, which is a popular family of libraries in the sort of Rust ecosystem. And then it's using this WASM or dynamic library file, as well as the CK file. And we're still using the WASM thing for witness narration with Wasmer, which is this fast runtime WASM in Rust. And proving is done natively with awkgraph 16, which is a Rust library in the awkworks family. And there's a Rust native API for things like initializing the library, proving and verifying, and dealing with input and serialization and that kind of thing. So once we have this sort of native Rust library, we then sort of wrap it in another library or consume it from another library with moprofify. So this is kind of dealing, responsible for talking across language barriers. So whether it's Rust and Swift or Python or Kotlin or whatever. And basically it's wrapping this Rust native API and deals with what's called like lowering and lifting, which is a thing you have to do when you're talking across two different language runtimes. So if you have a big num in Rust, it's not going to be the same as a big num in Swift. So you need to find like a common language to cross these runtimes. And the first focus on iOS and Swift. It says here easy to add Kotlin and Android, but thanks to Vivian, we actually have Android support now, so that's working. And React Native with native modules is coming soonish. So how do we build these complex cross-platform applications? And this is like not a new question, right? And the answer is basically unify. That's what Firefox came up with when they faced this problem. So what you do is basically you define all the business logic in Rust, and then you expose these bindings and sort of a thin wrapper to all these different language runtimes, so you can consume it. So that's what enables Firefox to have the same code base and application logic, and then just do slight differences whether it's desktop or Android or iOS. And in general, the goal, right, is we want to make it easy for developers who are writing applications or CK apps to sort of do this stuff, because they don't want to have to deal with all this tooling thing. So basically, we have this in the top left. You can see the UniFi interface that's kind of describing the interface and the logic of the API. And that's then generating the bottom left Swift API. And this is just like a native Swift API. So for the app developer's point of view, it's just like a normal Swift library. It's no difference. And this also means that you can test in isolation. So you can test Swift, Kotlin, and Python in isolation without having to deal with sort of the Xcode or whatever. Also, once we have this Swift native library or whatever, then you have to actually use it through Xcode to make an app for iOS or whatever. And that's like a different architecture. And there's a lot of things that you have to think about. You have to update the library and header files and so on. And we have a bunch of convenience scripts that make this easy for you, so you don't have to think too much about it. And I don't know, for people who have used Xcode, it can be kind of a pain to work with. So we're just trying to minimize that and just make it like any other kind of library. Here's an example of doing Catch 256, 150,000 constraints on iPhone. I'll talk a bit more about performance in a few minutes. And if you remember the diagram, I had like on the very left sort of the user, and I don't know if you could see, but it said like use has no brain. And it's like a joke, but basically users just want things to work. They don't want to have to think about all these stuff, right? So we want to make applications and user experiences that just sort of just seamlessly integrate into the user's daily lives, right? And you can imagine as a thought experiment, if you have like an Apple wallet or whatever, if you can use that with CK identity, that could be pretty cool. So this is this thing, response limits, response times, 3 important limits by this UX researcher called Jacob Nielsen. And basically this is kind of limits that are determined by human perceptual abilities. And he defines 3 limits. So 0.1 seconds for reacting instantaneously, 1 second for not interrupting user's flow of thought, and then 10 seconds for keeping the user's attention. And like at the very least, we should aim to keep the user's attention when we're creating these applications. And what about developers? So developers are humans too, I think. There's a bunch of them here. And they can only focus on so much at once, right? There's all this stuff, right? Like user experience and app development, libraries, architecture linking, Rust, CK, circuits, proving system infra, and there's no way they can do all of this, right? So it requires a lot of people, and kind of doing this takes away from sort of focusing on the business problem that you're actually trying to solve. So basically with mopro, what we're trying to do is splitting this up and create tooling so that developers can focus on their specific area of expertise. So going back to the diagram, right, you have sort of top right, Rusty Brain tooling and infra development. They sort of deal with all the tooling and Rust stuff. You have the CK Brain that's sort of doing circuit development, maybe a bit of Rust for some business logic, if it's like some Merkle tree or whatever you want to care about. And you have the Swift Brain that's doing app development. So they just like thinking about the app and making like a good user experience and maybe some Swift library stuff. And you don't have to think about the Rust and CK stuff. And then finally the user with no brain who just wants things to work. So I mentioned a design goal is like modularity. So it should be very easy to sort of add new platforms like Kotlin or Python or whatever. This also applies when it comes to proof systems. So adding new proof systems should also be easy. And a lot of the tooling and problems that you face are kind of similar. You have to deal with like FFI and serialization and packaging and so on. So you sort of solve them once, and then it's very easy to sort of add new things on top of it with the modular architecture. And it has a Rust core, which is kind of a selling point in the zero-knowledge ZKP sort of ecosystem, because it's like fast and secure and flexible, and lots of developers use it. And it's also built as a public good. So it's not tied to any specific product, which means it's not trying to optimize for a specific business use case or whatever. And this is thanks to a grant from PSC and Xerox PARC. So basically whatever is useful for people doing client-side proving, that's what we want. So where are we now? So this was actually a few weeks ago, but it was this hackathon at Dev Connect called CK Hack. And we did like 2.5 products, and one of them was Pocket Aadhaar, which is kind of CK identity for 1 billion users in your pocket. And it was taking this Anon Aadhaar product that I mentioned earlier, and then which is like this RSA verification of a signed PDF document, and then sticking that in a mobile app and doing native proving. And because the SDK they use is very portable, and it's kind of used for a web view, and then you only do the proving natively. We were able to do this in a weekend with Yannis from PSC, who was onboarded and dangerous in just a few days. So that's pretty cool. Another thing we did is we did Pocket Kimchi as kind of bonus product where it's a very hacky POC, but basically what we did is we added this alternative proving system called Kimchi, which is like a Plonkish proving system using the Mina blockchain, and we added like a very simple way of doing proving and verifying on mobile in just a few hours as a dirty POC, just to show how easy it is to sort of add new proof systems and platforms and stuff. So here's the Pocket example. So you have this signed PDF document, and this is like a web view where you upload the PDF, enter your password, and you can generate the proof. So how fast is this? So this is like on a real device, iPhone 14 Max Pro. Catalog 256, 150,000 constraints takes around 1.5 seconds. I try to find some comparable benchmarks for the same amount of circuits or constraints, and it seems to be like 10 to 20 times faster compared to comparable circuits in browser. It's pretty good. When it comes to Aadhaar, it's doing RSA verification, which is the same circuits in ZKML, if people are familiar with that. It takes around 6.5 seconds. The vast majority of that time is spent on witness generation, which is still done in WASM, and then actual proof time is like 2 seconds. So this is 10 times faster compared to a browser on a phone, which is pretty cool, because now we're actually below this 10 seconds barrier I mentioned before, and before it's basically unusable on a phone, so you can't actually do these proofs on a phone. So that's pretty big in terms of CK identity actually getting real-world adoption. We're walking around in our pockets with these phones that are like 1 million times faster than what we went to the moon with, so we should use that power in batch compute. Some bottlenecks, so loading the CK and the WASM witness generation are the most obvious ones. I'll just talk briefly about that. So CK is this thing when you're using Circum Snock.js, you have to load it in, and it's very slow. For large circuits, it takes like more than a minute. And basically what we have to do is we have to convert it to awkworks for the proving key and matrices and stuff. And we were able to speed it up by a factor of 10 by implementing this custom serialization format in awkworks. So it's now around 10 seconds. And the file size is also like halved, which is quite significant because if you have a large circuit, it's maybe like 100 megabytes and it goes down to 50 megabytes, which makes a big difference in terms of app distribution. We can load this in startup time, so the user doesn't necessarily notice it, but we still think we can do even more here, and this should basically approach 0. The other bottleneck is witness generation. So this is still in WASM. It's around 80% of the proving time. And moving to native here is like an obvious next step and like a big win. Shout out to Philip and Remco, who have been working on like this Rust library to make this easier, and we would expect to see a 10x performance increase or more. And with these two things fixed, then we should get to like 2-3 seconds proving time for Aadhaar, which is pretty good. That's basically like how you pay with a card or any kind of identity system you use. So it's comparable. So let's make CK on mobile great together. Where are we going next? So there's a bunch of things we want to do. We want to improve API and developer experience, make the sort of more robust API and better documentation, minimize the time to get started, and sort of make it easy for people. Performance, I mentioned the bottlenecks before. We also want to do some experimentation with GPU because we have GPUs in our phones, and like people are doing all this crazy AI stuff, and like we can get similar gains with specific proof systems that leverage this. We also want to support more platforms. So Android support we actually have now, thanks to Vivian who's over there, who's been working on Android support. So now you can do things on Android as well. We also want to do React Native models and add some more proof systems like Halo 2, Nova, and so on. How can you help? So there's 3 ways. If you're developing circuits applications, you can try it out and provide feedback. If you're developing a proof system, you can make it easy to consume for mobile and sort of make a clean Rust API, not launching any sub-processes, supporting serialization, small library size, and so on. If you're slightly more on the research side, try to have like constant or low memory usage and make it so that MSMs are sort of the dominant cost factor because that makes it easier to do GPU optimizations. If you're just excited about bringing CNR's proofs to mobile, you can help us build this tool. Come talk to me or check out the GitHub. Some acknowledgements. Vivian from PSC, UNREP over there, who's been helping a lot with building mopro and improving the developer experience and Android support and so on. Yannis from PSC, who built Pocket Aadhaar with me at CKHack. Phil Remco from WorldCoin for some great Rust code and some help. Ironman and Vac for continuing to build ZeroKit on our Leno mobile, and PSC and Serge Park for granted support. So, recap. We want to make proofs on mobile. Mopro is a toolkit for making proving on mobile simple and fast. And let's make CNR's proofs on mobile great together again. Future CK, the future is mobile, the future is now. Thank you.
Thank you. Thank you so much.
2 QR codes. Left one is for the GitHub repo and right one for the Telegram. Questions later, I think. Just come find me.